Well, hello! Welcome back. It's been a couple days since we've had a video, so let's get back into it. We've been talking about some scientific measurement practices. We're going to continue with that today and talk about a few specific things that you should look at as you're taking data in the lab. The first thing we're going to look at is accuracy and precision. And I know you guys all think that you're very accurate in your lab data, but sometimes there's some ways to test that. So accuracy is a measure of how close a measurement comes to the actual or true value of whatever is being measured. So how close you are to that real thing. Precision, on the other hand, is a measure of how close a series of measurements are to one another. So we've kind of talked about the importance of having lots of trials. Remember how we kind of talked about in a pharmaceutical lab, how you really hope that they do lots of tests before they give you some drug that could kill you? Well, accuracy and precision means a lot in that case. Okay, so we hope that they're doing lots of trials, and ideally, the accuracy of those trials would be how close it is to the real thing. You want everything to be as close as possible to what it should be. And we would hope that all their trials are also precise. If we have trials that are going here and there and there and there and that data's all over the place, then it's not very good data. So we want all of the trials to be very close together. So let's use a little golf analogy to examine this. If we think of the hole as being accurate, we want to get the ball to that spot. That's our goal. Then this one here, all of the balls are at the hole. So that means it is accurate. If we look at this one, all the balls are pretty far away from the hole. So it's not very accurate. It's away from where we want to be. And if we take a look at this one down here, again, all the balls are pretty far from the hole. Not very accurate. Precision-wise, remember precision is how close all those are together, then this one, 1, 2, 3, it would be precise because all of those shots were around the same area. 1, 2, 3, again, nice little grouping there. Very precise. This one, 1, 2, 3. Little more sporadic, so it's not as precise. If you're not much of a golfer, maybe you're a bow and arrow type person, archery. So let's take a look at this. Obviously, when you're shooting something at a target, you want to be in the center. So if we look at this one, all of the hits hit in the center, so it is very accurate. And there's a nice grouping there. They are all close together. If we look at this other one, again, there's a nice grouping together, so that would be precise. All of those hits are close to each other, but it's pretty far away from that center target, so not very accurate. And this one, shoo, 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 shoo. Man, this person was shooting all over the place. There's nothing in the center, so it's not very accurate, and there's shots all over. They're spread out all over, so it's not very precise. So let's try it with some real data, see how you do. If a student weighs a piece of metal for a lab, are his results accurate if the metal's accepted mass is 2.487 grams? Are his measurements precise? So accuracy, remember, is how close it is to the actual value. So if our actual value is 2.487, and we take a look at all of these trials that he did, most of those trials are pretty close. So I would say, yes, he's pretty dang accurate because there's only 0.001 that he's off on one trial. So that's pretty good. Are his measurements precise? Okay, remember, precision is how closely all these trials are together. So 2.486, 2.487, and all the rest are 2.487. So they're pretty close together. Only that 0.001 off again. So this is very excellent data, in fact. Everything's the same, it's precise, it's accurate. Right on, dude. He's got it. Or she. So let's try one more. To check the accuracy of a graduated cylinder, a student filled the cylinder to the mark of 25 milliliters using a more accurate tool. Is the cylinder accurate? And how precise are the measurements? Okay, again, accuracy, how close it is to the actual. So we have 25 milliliters is what it should actually be, and this is how much it read. 26, 26, 26. It's about a milliliter and a half off each time, which isn't bad, but it's not the most accurate. So I'd say maybe this isn't as accurate as it could be. Precision, again, how close they are to each other, 26.54, 26.49, they're all kind of within a tenth of a milliliter. So that's pretty good. So I'd say that these are precise, but not that accurate. Oh, unfortunately, it's a sad day, but there's always error in your experiment. We've kind of talked about this before, that nothing is ever perfect. And we can actually measure the error in something called the percent error. So the accepted value is always going to be the correct value based on other references. Sometimes we get that from a book, sometimes it's been standardized somehow. So we always have something that's accepted more than what we actually measure it. The experimental value then is what you get in the experiment, what you experimentally determine. So the difference between these is called the error. Now to turn it into percent error, we take the absolute value. So remember, your error is your experimental value minus your accepted. And so then to find the percent, we're going to take that experimental minus the accepted divided by the accepted times 100. You might want to write this down somewhere, by the way. So let's practice using this. What is the percent error if a student found the boiling point of water to be 99.1 degrees Celsius? So our experimental value is what the student actually found in the lab, 99.1 degrees Celsius. Our accepted value, if we think about the boiling point of water in Celsius, is 100. So if we take 99.1 minus 100 divided by 100, and then we're going to take it times 100% to get it into a percent, then we end up with a 0.9% error. Now that's pretty good. Typically, anything under 5% is a really excellent percent error. Anything above that, you got a little work to do on your lab technique. But don't worry, I've seen errors as high as like 500%. Sometimes things happen and you just can't control it. Alright, and the last topic for today, uncertainty. When we are measuring things, you should always measure it to one more place than what is shown on your measuring device. So this means on a graduated cylinder, you can see the lines, you can estimate in between those lines. If you have something like this where it's a meter stick, we have 1 meter is what it is measured in, so we can measure to the tenths place because this meter stick is shown in the ones place. So one more place past that would be the tenths place, and we could measure to 0.06. If it had even more markings, again, this is still a 1 meter stick, but it has some markings dividing it into its tenths. That means that we can measure one more place and measure it to the hundredths. If it had even more lines, like most meter sticks do, again, this is a 1 meter stick, it has tenths, it has hundredths marks, and so we should be able to go one more place to the thousandths. Whenever we are measuring that extra place, it's always uncertain because it's obviously not shown. It's our measurement. We're just estimating. And so you can put this uncertainty on by putting 0.6 plus or minus 0.1 because you estimated that mark. In this one, measured length 0.61 plus or minus 0.01 because that's how much you measured, or that's how much you estimated. And this one, 0.06 or 0.607, being dyslexic today, plus or minus 0.001 because that's the place you estimated. This doesn't always have to be to that estimated part. Sometimes you're really uncertain about your measurements, so you change what this is. However certain you are, that's the uncertainty that you would add to it. So that is all for today, and I will see you in next class. Again, if you have any questions, feel free to email me or send me a message on Schoology. We will see you later. Signing off.